All right. So it's a great pleasure to have Kantaro Ohmori from Weekend Items, and he'll talk about symmetry spans and enforced gaplessness. Please take it away.
Okay, thank you for coming and thanks for introduction and for also for inviting me to talk about this. So I'm Kantaro Mori now at the Weekend Items, and I'm talking about the symmetry spans and enforced gaplessness, which is a collaboration work with Takamasa Ando at the Yukawa Institute at Kyoto University. And the paper is this, the archive number is this. Okay, so introduction and the theme of this talk is to connecting the macroscopic physics model and the microscopic physics or model. So microscopic physics phase and the macroscopic description or model. So one traditional way to think about it is given a microscopic model, and we wonder what is the phase of the model, or what is the microscopic behavior of the system. Or if you have something particular, some particular macroscopic phenomena you want, and then try to cook up some microscopic model that should realize your desired properties. That's the other direction. So either way, that's a very natural questions to ask for in physics. And in this talk, I'd like to focus on a particular property, which is gaplessness and gapness. So as you all know, that we call the system is gapless when there is a excitation with an infinitesimal energy, and it's gapped otherwise. Okay, so that's the main question. And the symmetry is a canonical tool beyond the perturbation theory to to talk about or analyze that problem, because the symmetry is preserved under the RG flow. So if you have UV start from the UV theory and then follow along RG flow to the IR description, and then you can also think about the symmetry of the UV system and the symmetry of the IR system. Then the crucial, so the importance of symmetry in this context arises from the fact that there is going to be a map from UV symmetry to IR symmetry. So that's the induced by the RG flow. Okay, and the okay, so via this map, the microscopic symmetry should also act on the IR theory. So that in that way that we can either analyze the possible or constrain the possible IR phase, because it should admit the UV symmetry action, or like uh, starting from the desired IR phase and then analyze its symmetry and then try to cook up UV model that has a full symmetry, has a non-trivial map to the IR symmetry. So both way symmetry is very important. And of course, that fifth ternary matching is the primary and prominent example. So in the case of symmetry to be just continuous, and then also with carrying perturbative anomaly, then Fifth famously argued that by anomaly matching, the system has to be gapless. So that's the primary example. But the natural question here is that whether there's other properties of symmetry. Is there any symmetry way to enforce gaplessness other than to fifth anomaly for the continuous symmetry? And the upshot of this talk is we found a new criteria, a symmetry-based criteria that enforces gaplessness. And the point is that we impose the two symmetries rather than one, and that shares subsymmetry. So the C and D are some symmetry acting on your system, and then but it shares E. Okay, so that I call symmetry span, and the span is the name of this diagram in the category theory. So this shape of diagram is called a span in category theory. So I call it the symmetry span, and not all symmetry span, but there are particular case of symmetry spans that we can show that there is no compatible TKFT. So there is not TKFT admits this kind of action by the span. And by this, we can so exclude such a TKFT, IL TKFT fixed point, imposing that kind of symmetry span. Okay, so if you find such symmetry span in your system, then you can conclude that the IR must have gapless excitation, or maybe a non-TKFT, non-CFT exotic phase. But the rest of the talk I'll be a bit sloppy and just say the gaplessness. Now, also the one selling point of this criteria is that this is directly applicable to lattice system. So these C, E, and D is going to be something that we can exactly realize on lattice rather than the fifth. So that's in the contrast to fifth anomaly matching, because it's widely believed that the continuous symmetry with the perturbative anomaly is not realizable, exactly realizable on lattice. Instead, here it's going to be the symmetry span is going to be realizable on lattice. But nevertheless, there is going to be example suggests that we will see that there is going to be a relation to the fifth anomaly anyway.
Sorry,
I will comment about that. Yes.
can I ask what do you mean by this exotic non-TFT, non-TFT phase?
There's some like fractal phases, so that I don't.
I see. Okay.
That yeah. So that's not TKFT, but yeah, maybe gapped
But if
fractal phases. So,
if the underlying system is relativistic invariant, then you can exclude it.
yeah, yes.
Thank you.
So is there some constraint in the sense objects in D or defects in D that are not in E, can they also be in C? Like, or do they have to be like mutually exclusive embedding to C and D?
So yeah, so so the image of E which has to be identified, so that should act on the system in the same way, and yeah, I will comment about that. But yeah, maybe the question is that the other whether the like action of C and D commutes, or if that's the equation, then it doesn't commute in general.
So for instance, junctions in C can be charged under defects in D, which would be some kind of anomaly, or
Oh yeah, that's possible. Yeah, yeah. So I only impose this structure. Just you have to symmetry that happens to shares common subset symmetry, but I don't say anything more. Yeah.
I see. Thank you.
So what is the full symmetry of the UV theory? Is it just a times D?
No, so yeah, I will also comment over that. So it's the full symmetry is it depends on what you mean by full symmetry, but yeah, it's going to be way larger than C or D in the case that you can say gaplessness. I will comment more on that later. Yeah. Yes. Okay, so the introduction is done, and in the rest of the talk, I will talk about some background stuff, and then I will talk about the main part, main criteria, and then talk about the example. So I think everyone in this seminar knows use this paradigm that the general symmetry is all topological operators in the system. So in this talk, I focus on the fully topological operators, and then by this definition that the RG flow invariance or the preservation of the RG flow is kind of automatic, because you can if you have a topological operator in the microscopic system, then you can just inflate it to arbitrary scale, to the macroscopic scale. So you conclude that the macroscopic scale, you should have the same set of topological operators with the same properties. Okay, and in the rest of the slide is just a recap that the reminder that so mathematically for finite symmetry, it's kind of well understood, and in particular in 1+1D, it is just a fusion category. And for invertible case, it's a so-called H-graded vector spaces with a twisted with anomaly. And for the continuous case, it's the precise mathematical structure is a bit more complicated, but there are progress. And on lattice, of course, there's different kinds of subtleties, and so here I just say that so there are subtleties in the continuous and lattice case, in the mathematical treatment of these general symmetries, but I just gloss over it and pretend that there's going to be some nice framework. Yes, and okay, and and okay, so then the crucial thing in the rest of the talk is that how to understand the gapped phases when the symmetry is imposed, the general symmetry is imposed. And so going back to this diagram, that if you have a symmetry in UV, then it should also act on the IR system. And here we take the IR to be this TIR to be the fixed point. Okay, so if it's in the gapped phases, and in particular described, the large distance physics is described by topological quantum field theories, TQFTs, then we are going to, and then this IR fixed point is a TQFT with a SUV action. So we are interested in. So TIR is going to be SUV TQFT, SUV symmetric TQFT, and so in this talk I denote this the set or two category of the TQFT, symmetric TQFT with this symbol or TQFT of S. Okay, and mathematically, at least in the fusion category case, it's established that TQFT of S, so a set of S symmetric TQFT is the same thing as the set of the S module category. So that's there's a nice description. Okay, so this is a module category of S, and so at least for the finite fusion category case, it's established, and we can do even the classification of possible gap phases in that case. We don't need classification necessarily, but it's a nice thing to have. And so, for example, for just one finite invertible group symmetry in 1+1D system, then it's H-gapped phase is in one-to-one correspondence to the gauging of possible gauging you can do within H. That's like a condensation philosophy. And so then such gauging is characterized by a subgroup, the choice of subgroup of your H, and also like choice of discrete torsion, which is a Tuchel cycle that trivializes your anomaly after pullback to K to subgroup. Okay, so I denote this corresponding module category as this because the H because each vacuum is in one-to-one correspondence to the coset class. And so in that sense that this is a vector space graded by coset, and then there's a twist. So this in physically, of course, this module category describes or corresponds to the phase where the H symmetry is broken down to K, and if you focus on K, each vacuum looks like a KSPT alpha. So that's the phase. And so the example, just take it the simplest case of H equals to Z2, then of course there are just the two phases of the SSB phase and non-SSB phase. But these are the so-called the simple modules or simple TQFTs, which doesn't account for the accidental vacuum degeneracy. So there might be additional vacuum degeneracy that's not counted by Z2. So if you take into that possibility into account, then the set of the Z2 symmetric TQFT or the set of Z2 module categories are like can be denoted like this. So this is just a set of like generated by spun by these two phases, the SSB phase and trivial phase over spanned by n. So in general, you can have n1 copies of n1 pairs of SSB phases and n2 copies of the symmetric phases. And n1 and n2 are just random independent integers. So that's the most general gapped phase you can get for the Z2 symmetric system. And for the Tambara-Yamagami or chromosome duality symmetry, so I think this is also familiar to you guys. So the Tambara-Yamagami Z2 category has a Z2 symmetry and also the duality defect with this familiar fusion law. And the famous fact is that the only simple module of this symmetry is itself. And so the so-called regular module. And the regular module describes the full SSB phase, namely the vacuum in one-to-one correspondence to the simple objects in the original symmetry category. And also the symmetry action on the vacuum is just the fusion load. Okay, so that's the only simple module, and then there might be accidental degeneracy. So the most general Tambara-Yamagami symmetric TQFT is just the copies, direct sum of itself. So just copies of this triple. That's the most general thing. And okay, so in the span story, it's going to be important to talk about this pullback or the restriction to subsymmetry. So assume that there's some subcategory into larger embedded into larger category. For example, just thinking about the Z2 symmetry naturally embedded into the Tambara-Yamagami category. And then we can, so corresponding to such functor, there's a corresponding pullback functor or pullback map from the TQFT of the larger symmetry to TQFT of the smaller symmetry. So this is just restricting or forgetting the symmetry into the smaller. Okay, so in this particular example, okay, so as I said, that the only simple module for Ohmori Yamagami is itself, and if you forget about the D, then you only remember the Z2 action on the vacuole, and Z2 action on the vacuole is this. So this ket eta and the ket 1 are exchanged by Z2 action. So this Z2 broken thing and broken vacuole, and this is a Z2 vacuole. So just as a Ohmori Yamagami itself as a module category and pull back, then we get this direct sum of like SSE vacuole and asymmetric vacuole. And that, okay, so, and the point is that we always get the same numbers of symmetric vacuole and the pairs of SSE vacuole. That's, of course, because that the chromosomal duality is exchanged to the chromosomal duality sends the high temperature phase to low temperature phase of Ising model. So it exchanges the SSB phase and the Z trivial phase. So you should be getting in pairs. Yes, that's very simple fact. And okay, so so as an equation that if you put the whole set of TQFT of Ohmori Yamagami and taking the pullback, so just forgetting about the chromosomal duality, then the image is this. So that's as I said, that you get always the same number of symmetry vacuum and the pairs of SSE vacuole, and that's not the whole of the whole possibility of TQFT, Z2 symmetric TQFT. So that the image is the proper subset. Obvious fact is going to be important. The last ingredient I need for the symmetry span story is the continuous symmetry. So for continuous symmetry, the we all know that the Number-Goldstone theorem tells us that that for a connected group element to be spontaneously broken, if a connected element of your group, continuous group is spontaneously broken, and then there has to be a gapless element. So that's the Number-Goldstone theorem. And so for connected G, and for then if we assume that the IR phase, if we want that the IR phase is gapped, then we cannot allow any SSP, and therefore this is kind of assumption, but I assume that for continuous symmetry, then the only possible gapped phase in terms of G is just SPT or direct sum. So there might be multiple vacuole, but each vacuole looks like just a GSP. So there is no just simply there is no way that this connected group can permute the vacuole. Okay, and so one way, this is not the original way, but one way of argue for the fifth claim is that if the G is anomalous, then we say that there is no SPT, and then we've already said that the only possible gapped phase is basically SPT. So combining the anomaly and this fact, then we can say that there is no TQFT. Okay, so that's one alternative way of arguing the fifth anomaly matching. And So if you have another structure to prohibit this kind of GSPT for the continuous connected G, then we can also say that there's no TKFT phase. And so the anomaly case is some intrinsic property of the symmetry that prohibits no SPT. But the idea is that instead of trying to find instead of an intrinsic property, maybe we can impose other symmetry. So that's the extrinsic structure to prohibit the GSPT. So then, so if we can do that, then we are going to exclude the possibility of TKFT in the IR. So that's the strategy.
Sorry, Kantaro,
Yeah.
can I ask the question?
Yes. Yes,
Can
yes.
there be a GSET in this set?
So I think, I mean, so of course for the discrete symmetry, the finite symmetry, of course, yes, there can be. Oh, you're asking about okay, so in higher dimensions, so yeah, that's a nice question. Here, okay, I was secretly thinking of the 1+1D in higher dimensions. Indeed, there can be, of course, the non-trivial GSET that can match the kind of also there can be a non-trivial anomaly that matched by TKFT. So yeah, so in higher dimensions we have to be careful about that possibility. I do agree, and so yeah, but still the I think the fact persists that it's kind of there's not many ways that G can act on the gap TKFT. So assuming the continuous symmetry is going to be exclude a large set of TKFT. So that's the that philosophy. But you're absolutely right that in higher dimensions be careful about non-trivial GSET. Thanks.
Makes sense. Thanks.
Yes. Okay. Is there any other questions? Okay. Then I'm going to the main topic. So main topic is the symmetry span. So as I said, the symmetry span is just this diagram of symmetries. So you have C and D, the two symmetries shares one subsymmetry. Okay, and then yeah, so here I also have this part. So assuming that your system has a symmetry C and D, that means that it's also acted by the larger symmetry generated by C and D. So it's like alternating a word of like CD, C1, D1, C1, C2, D2, C3, D3 kind of that kind of action you can compose and that such words, every word is going to be symmetry of your system. So that's some very large symmetry. And then it's more natural to think about just the faithful part or faithful projection of such words. So that's S phase. So just I'm saying that assuming this symmetry span means that you're assuming something larger, and the C and D that doesn't necessarily commute. So that can be very large. And so one way of thinking of it is just take the universal one. So just taking all the words like the C1, D1, C2, D2, blah blah blah, and imposing no relationship other than that the E is shared. Okay, so that's a kind of universal one. I don't know how to do it in mathematically precise way, but it's probably doable to define such symmetry. But that's very big, and that's very very big, and yeah, and in many cases it's not phase-free acts on the system, at least in the continuum we will see. So if you want to talk about more familiar kind of smaller faithful symmetry, then that's of course depends on the system. So so here I'm just saying that it is true that there's going to be a larger symmetry of the system that's generated by C and D, but to analyze that symmetry anyway, it's just effective to focus on the generating sets or generating things that's a C and D. Okay, so this is in this slide I'm just saying that the rationale for focusing on the symmetry span rather than trying to find the actual whole thing generated by C and D. Okay, so that's just a strategy.
Okay, can
But
I
yeah.
ask a question?
Yeah.
Instead of considering this universal push out, is there a sensible notion of the smaller symmetry that can include the two and can fit into this diagram?
So yeah, so there are so the push out is a universal one, and anything. The definition of push out is that anything fits here admits functor or map from the push out onto that. Yeah. So of course there are various possibilities that you can.
But is there a concept of a unique symmetry that is the smallest one that can fit there instead of this very large one?
No, I don't think so in that way. Yeah, usually, yeah.
Okay, thank you.
Yeah. Yes. So, okay. So anyway, let's assume that your system has this kind of automates the symmetry span action or equivalently some symmetry that sits here, and then also assume that your system is described by TKFT in the large distance. So then you have your TIR is a TKFT and it's here. And then so you can forget starting from the phase of symmetry, full symmetry, then forget onto C or forget onto D. So this is just forgetting about into the smaller symmetry. And then also like forget further to E. So that's a further subsymmetry. But of course, it doesn't depend on whether you first forget to C and forget to E or first forget to D and forget to E. So this square diagram also should commute. So you have a TTR here, and then if there is a TIR here or some TKFT here, then there has to be a pair of C symmetric TKFT and D symmetric TKFT whose pullback image matches. So they taking a control position, and then if there's no such pair, so if the intersection of the image of pullback is just zero, zero is a zero as a theory. Then there's no symmetric TKFT. Okay, so and this is a relatively easy checkable condition, as we will see. That's the logic. And so in the most of the rest of the talk, I will focus on this kind of setup. So in particular, the symmetry span of this form, just having, so C is some fusion category, the finite symmetry in 1+1D. And then this E to be, I assume E to be just some invertible symmetry, finite invertible symmetry, and that's embedded into continuous symmetry. So G, further I assume the G is connected, so some connected symmetry. Mostly just U1 or product of U1. Okay, so then, as I said, that the TKFT of G here is just bunch of SPTs, so the direct sum of SPTs. So putting back that here also like the as H TKFT, it also has to be direct sum of SPTs. And then the question is whether such a direct sum of SPT is in the image of like Probak map of IC star. So just you can realize if you further, yes.
So you're assuming both G and H are continuous.
No, I assume G is continuous.
Okay,
I mean,
so
H is
H is
H is fine. Yeah, but it's already like GSPT, so like restricting to yes.
Sorry, so you say G is continuous, and what do you mean by vector G?
Oh yeah. So that's a very sloppy notation. That's some
So it's not to interpret it like literally as a category.
Yeah, it's not literally as a not literally as a category. Yeah, that's some version of nice version of it. So you can use a skyscraper sheaf or some sheaf theoretic things, I assume. But yeah, the detail doesn't matter here. Like I just wanted to be coherent rewrite things. So just that.
Okay, thanks.
Yeah. And okay. Any other example? Any other questions before going to examples? Examples. The example of span is this. So you just taking the Tambara monogamy Z2 and thinking about now assuming that it's Z2 subcategory, so just the invertible part of Tambara monogamy is actually embedded into U1. Okay? And I assume that this U1 is non-anomalous. If it's anomalous, then there's nothing to talk about. So I assume it's non-anomalous. Then, as I've already said, I assume that the chromosomal duality, so as Z2 symmetric phase, there has to be the SSB phase and the symmetric phase has to come in pair. But that contradicts with the assumption that the Z2 is embedded into U1, then this SSB phase cannot be realized as a gapped phase because then Z2 is in a connected element in U1, and so Z2 is broken, then the generator also has to be broken, and then there's going to be a number Gaussian mode. Of course, in 1+1D, Marmin-Wagner also says that there isn't gapless. Sorry, there isn't a continuous symmetry SSB anyway in relativistic system, but anyway, yeah, in either way, we can exclude the U1 SSB. So these two contradict. So there is no intersection, and then there is no span symmetric TTFT. Yeah. So if you have this kind of symmetry structure in your system, then you immediately conclude that the IR is not a TKFT. And the example of such theory is just a compact boson at special radius, so the square root 2 times self-dual radius. So here the U1 symmetry is just a shift symmetry, and then it's famously known that at this special radius, then this system also has the Tambara-Yamagami symmetry, just coming from just gauging Z2 and then taking TDO and then coming back to this radius. Okay. Okay, so then using the argument I proposed, we can say that the system is gapless, which is obvious in this case. This is compact boson theory. But nevertheless, it's interesting to see what's happening here. So here, so in this case, actually this assuming this Tambara-Yamagami and the U1 shift symmetry generates the winding symmetries. If you do this composition of like duality and shift symmetry duality, then you basically generate the winding symmetry. Okay? And of course the winding symmetry and the shift symmetry has a mixed anomaly between them. So yes. So in this case, this symmetry generates some symmetry that includes the U1 squared with a mixed anomaly. But the point here is that I did not assume this mixed anomalous continuous symmetry, but in the span, there's only a non-anomalous symmetry, but it was generated by the span. The mixed anomalous continuous symmetry is generated by the span. That's what's happening here. Okay. But so I said that the symmetry span is good because it is realizable on lattice. So there is a particular precise lattice version of this story. So instead of continuous theory, we can think about just a spin half spin chain, and then there's a usual Tambara-Yamagami Z2 chromas-1 duality symmetry on this. The usual very familiar action of the and this okay. So for on lattice, of course, this paper says that the symmetry category, whatever it is not the fusion category. So we cannot just use what we've said. But still, anyway, that the chromas-1 duality, this D is a chromas-1 duality that exchanges the Z2 symmetric phase and Z2 broken phase. So that's coming from Z2 gauging. So I think we can convincingly conclude that although there's a not complete mass theory, but we can at the physics level conclude that in that like Tambara-Yamagami symmetric gapped phase, there has to be an equal number of symmetric Z2 symmetric vacuum and pairs of Z2 broken vacuum. Yeah, this, and then the rest is the same. So if you further impose U1 symmetry, like Z2 is embedded in U1, then this part doesn't fit. So we expect the system to be gapless. Yeah, and yeah. Okay. So for in this case, we take this U1 to be generated by this charge. Sum is just sum of x, and the one Hamiltonian that commutes both with this chromas-1 duality action and this U1 action is this by zy, and this is XX chain. If you conjugate this Hamiltonian with x at all the sites, then you get y plus z0. So that's XX chain. And of course, it is already noticed that at least these two papers noticed in the study the XX chain that having both the U1 symmetry and the Cronus one theoretic symmetry. And also now it's also known that the XX chain flows in the continuum limit. You get back the compact boson at this. Okay. So on lattice, what happens is more interesting than on continuum, and also this also of course noticed by these papers. So and the okay, I hope. Yeah, but anyway, that the so similarly to in the continuum, we can study what is generated by this U1 symmetry and D, the chromosome duality symmetry, and then what's generated is this U1 charge. So this is a non-on-site U1 charge, which automatically also commutes with this Hamiltonian, and then these two is famously generates the so-called the on-Sag algebra, which is an infinite dimensional D algebra. So okay. So on lattice, these two symmetries generates something very big, and that's at least contains the on-Sag algebra, which is infinite dimensional D algebra. So it's not just continuous; it's infinite dimensional D group, and so it's very big. But that's on the RG floor. Just collapse onto the two U1s, okay? With a mixed anomaly. Yes. So that's what happens. Okay? And so, yeah. So that's what's happening here, and yeah. So this structure is in the sense that precisely the lattice version of what we've seen on the compact boson. Yeah, and there's a ZN version of the story. So so instead of the qubits, we can think about chain of qubits, and then so with the Heisenberg finite Heisenberg algebra acts on it, and then there's a ZN version of Chromosome Tamburian action. Then we can impose this U1, and whose ZN subgroup is generated by X. Yeah. So if you impose Q and D, and then Q prime, this thing is also automatically generated by these two. So, and it's also known that these two generates the same on-Sag algebra as before. Also, this paper showed that there is a Hamiltonian, this thing that commutes with D and Q, and therefore Q prime. Q prime. So this Hamiltonian commutes with the entire on-Sag algebra, and also the chromosome duality symmetry. Okay, and because it commutes with on-Sag algebra, so it's integrable, and so they already analyzed the system, and it seems to know that it's gapless, and central charge is 1 or this number. But here we can to just saying that it's gapless in the IR, that we can just circumvent that integrability analysis and just use this part of span. Okay, so that still doesn't involve any kind of infinite dimensional algebra. Okay. So that was the end chain. And then we can also generate other examples unrelated to, well, not directly related to Tamura-Yamagami. So, and even there's just the invertible case. So here we take type 3 anomaly for the Z2 cubed, and then pick the Z2 subgroup, which is non-anomalous. And assume that these Z2s are embedded into U1 square. So then so then because Z2 squared is embedded in the U1 squared, so it has to be preserved. It cannot be spontaneously broken. And then thinking about this part, so because this Z2 squared part, Z2a and Z2b cannot be spontaneously broken, but there's a type C anomaly, so the third Z2 has to be broken. But because of this anomaly, that's the sum of two different SPTs. But this U1, so in this case, I use this is U1. So U1 squared has just a single deformation class of SPT. So the pullback of that's trivial U1 squared SPT is just a single SPT. Okay, so this pullback image has to be just generated by a single SPT. Okay, and that there's a mismatch. So in this case, a bit more subtle, that the image of pullback along IC, so image of IC star does have a like direct sum of SPT, but the two different things, and that's not compatible with this part. Okay, so that's also enforces the gaplessness. And the concrete theory is automating this thing is a spin for level 1 WCW model, or equivalently, it's just two copies of Dirac fermions, and we can also do this on lattice.
So is there something special here about taking two Z2s instead of only one besides to the power 3?
Yeah, I think if you take only one Z2 and then embed it into U1, then I think you can, then you can, because yes, then you can break the both Z2. So there can be 4 vacua. That's compatible. So you have to take two of them. Embedded into U1.
It's complicated, but you can think about it. Thank you.
Yeah. And so there is a related example of it by a Kennedy-Tasaki transformation from this, if you know about it. But so in this case, we take the same Z2 squared embedded in U1, but instead of type 3 Z2 cube type 3 anomaly, we can also embed it into rep D8. So in this case, that this thing is the rep D8 is non-anomalous in the sense that it automates SPT, and this is non-anomalous by definition. But the whole thing is kind of very anomalous, that and can enforce gaplessness. Yeah, and in this case, very subtle, and actually depends on the choice of functors here. but there's a particular choice of functors that there is no compatible SPT or sum of SPTs. Okay. Yeah, and so yes, and the example is just U1 squared, U1 level 4 squared, and on lattice is just a XX chain. And here is just I haven't any kind of any serious analysis about this, but we can also think about at least on the continuum. Just think about the Maxwell theory, and so that's just the 3+1D version of a compact boson. So it has the same structure of the Tambarem-Mogami of like gauging the one form zeta subgroup of one form symmetry, and yeah, so this structure, and yeah, and yes, so here we have to use the one form version of Navier-Stokes theorem. Anyway, I think the so it's the same and we can apply our argument. Oh, of course, this is Maxwell theory, so we all know that it's gapless. But so I think it's interesting to try to do a lattice version of this this example, which I don't know how to do it. Okay, and so the patterns in all the examples is in the continuum. This S face that sits on the bottom right corner of the square contains a continuous G symmetry with anomaly. And then on lattice, so if you realize it on lattice, then it has a on saga or on saga like algebra, which is infinite dimensional the algebra. And then in the continuum limit, this latter thing is collapsed to the former thing. That's the pattern I see in the examples where the symmetry span exists, and that enforces gaplessness. But I don't know why that's whether it's always the case. No. Okay, so in summary, so I presented the symmetry span criterion for the gaplessness. Okay, so if this condition is satisfied, we're just analyzing the possible symmetric TQFTs. Then we can, in some cases, we can conclude that there is no asymmetric TQFT acted by symmetry span. And yeah, so there are many open questions, and the first one is I've already said. The second one is just to create more lattice examples. So far, the examples I gave you lattice examples gave you mostly just bosonization of some free fermion system. And the one exception is this the U1 invariant clock model, which is integrable. But yeah, so the natural question is there any more variety of things? And is there any systematic way to, so the hard part, so the part to find this new symmetric span that enforces gaplessness is kind of easy. It's but the part to find the actual Hamiltonian is harder, and I don't know how to do it in a systematic way. So that's some very practical problem to think of. Yeah, and also like to try to find the examples in the higher dimensions, especially on lattice, will be very interesting. So I stop here. Thank you for the listening.
Hey, thanks a lot. Other questions? Let me start by asking a question. I think I've asked you this before. So one obvious question is, do you need to have C and D, but one of C and D be continuous? could there be two finite fusion category symmetries which form a span, and then some anomaly in S phase that then triggers this gaplessness? Have you any examples like that?
I do not.
Are they ruled out?
Well, yeah, I don't have any concrete argument against that neither, so I don't know. My sense is that probably for the just a finite thing, then it's kind of, well, at least in the 1+1D, the TKFT is just kind of just number of vacua. And kind of my sense is that you probably find some lowest common divisor thing, in a sense. Like, yeah, but I don't have any solid argument. Yeah. So I feel it's probably no, but I don't know.
But sorry, is the universal push out for two finite symmetries also finite or not?
No. So, well, it depends on the pitch category. Yeah. So it actually depends on pitch category you are working on. But if you are like just a finite symmetry in a group, not abelian group, but just a category of groups, and then the push out is for the two push out for the two finite symmetries, so-called a free product. So that's, as I said, generated by just the wars, the arbitrary wars, alternating wars. So that's infinite group.
Okay, it's infinite, but it's still discrete, right?
Yes. So that's still discrete.
Because sometimes you break it, you get infinitely many vacua, but not constant bosons.
And actually, another question I had was, in your examples, you always had this the statement that as faithful contained U1 times U1 with anomaly, but you never actually, I guess it really depends on the specific model, but in these lattice models, these Onsager algebras, these are actually, you're also saying they're contained, but so there's a larger symmetry that acts faithfully, or
almost. It's just a Onsager algebra and this D.
And this D. And then together, that's the full symmetry.
Yeah. I think so.
Okay. All right.
I mean, it generated by the two, of course. Yeah.
Okay. Any other questions?
Kantaro, I have a related question. So if you have on this slide, if you have Q and D, then I think it's quite clear that you have to have Q prime, and therefore the Onsager.
Yeah.
But if on the lattice, if I have Q and Q prime, do you know if that necessarily imply there has to be a non-invertible symmetry?
No, I don't know. So for the ZN case, this is the only Hamiltonian I know of that commutes with Q and Q prime. So I have no idea. I've thought about trying to find I mean systematically find other like more longer complicated Hamiltonians, but I haven't succeeded. So
okay, thank you.
Okay, no more questions. Then I say we thank Kantaro again.